Hello, dear students. In this session, let us discuss about geometrical isomerism. So, before we start the actual discussion on geometrical isomerism, let us know what is isomerism. It is a phenomenon by which all of you know organic compounds exhibit same chemical formula but different structural formula. We call that as a phenomenon called as isomerism, and the compound which exhibit isomerism are called isomers. So these are the two examples of isomers. We can see both of them, they have got the same molecular formula but they differ in the structural formula. There are different types of isomers which we can see from this chart. The classification of isomers. Isomers are broadly classified into constitutional isomers, which we call it as structural isomers, stereoisomers, which we call it as optical isomers. So in stereoisomers we have distereomers and enantiomers, and in distereomers we can classify as cis-trans isomers, and in stereoisomers we have one more type, that is conformers and rotamers. So these are the different examples. See, say for constitutional or structural isomers we can give this example, and for cis-trans these are the two examples which we can give, and for enantiomers this is an example, and for conformers this is an example. So like this we can give the broad classification of isomers. And let us discuss about what are stereoisomers. So in this we can see the atoms which are making the isomers are joined within the same order, but they possess a unique spacing. So geometrical isomerism is one of the form of stereoisomers, and more specifically from the above diagram we can understand that most of the compound exhibit geometrical isomerism, which we also called as cis-trans isomers, and these fall under a category distereomers. So if we want to discuss in detail about the geometrical isomers, some molecules have the same molecular formula but they have different spatial arrangement of atoms in space within the same molecule. We know these are called as isomers. So these geometrical isomers occur when we have a restricted rotation in somewhere in the molecule. So compound which can exhibit one set of physical properties when arranged in a particular manner and can exhibit another set of entirely different physical properties when arranged in the other. So such thing we can observe in geometrical isomerism. Geometrical isomerism falls in under what is known as stereoisomerism. So geometrical isomerism is isomerism which arises when atoms or groups having different spatial arrangement which are observed due to the restricted rotation of bond or bonds in a molecule. Okay, this restricted rotation mainly occurs usually in a molecule which contains carbon-carbon double bond. So what we can say, whether it is possible with carbon-carbon single bond. So in carbon-carbon single bond there is unrestricted rotation about the single bond. Say for example 1,2-dichloroethane. This can be represented structurally like this. So it is not an isomer because we can get the above configuration just by twisting the carbon-carbon single bond. Nagu, nagu, ಹೇಳು. So, in this case, in case of 1,2-dichloroethene, we can see tris trans 1,2-dichloroethene and cis 1,2-dichloroethene. These are the structures which are obtained by the rotation of double bond around carbon-carbon atom. So, the above compound 1,2-dichloroethene can be represented by two configurations. So, this is because two structures above the two configurations are not same, because the rotation around the carbon-carbon double bond is restricted. The two configurations may look alike, but they are not same. So, hence they are isomers. So, when the two chlorine atoms are locked on the opposite side of the double bond, then the compound forms trans isomers. When the two chlorine atoms are locked on the same side of the double bond, then this is called a cis isomer. So, here the trans means Latin word across or transatlantic, and cis is also from the Latin word from the side. So, if you take another example, 2-butane having the two configurations. So, now we can see trans 2-butane and cis 2-butane, wherein the two methyl groups, if they are lying on the locked on the opposite side, then it is trans. If they are on the same side, then it is called cis. Okay. So, when the two methyl groups are locked on the opposite side of the double bond, the compound forms trans. When the two methyl groups are locked on the same side of the double bond, then it is called as cis. So, organic compounds must satisfy the given condition to form geometric isomers. The first one is restricted rotation. Okay. That is often involving carbon-carbon double bond. Presence of two different groups on the left hand side of the double bond, two different groups on the right hand side, then we can see it is not necessary to have the similar kind of groups or atoms on the both the sides. So, let us take the example of 1,1-chloroethene, which can be represented like this. In spite of swapping the right-hand group, the molecule of 1,1-chloroethene still remains same. So, on turning the entire model of left-hand side to about 180 degree, the same configuration of the molecule is on the right-hand side also. So, geometrical isomerism is not possible for this with this. So, this is the three-dimensional view of the same molecule. So, if we think of two different groups, okay, say for example 1-bromo, 1-chloroethene, which can be represented like this. Okay, this is a modular view of that molecule. In the above, blue and green groups are on either side of the double bond or on the opposite side. And all the groups around the carbon-carbon double bond are entirely different. So, they form geometrical isomer. The cis-trans configurations are meaningless, having different substituent around the carbon-carbon double bond. So, for this, the more sophisticated one, EZ notation comes in. So, this is a dimensional view. The presence of double bond, carbon-carbon double bond, restricts the bond rotation, which is a necessary condition for the molecule to exhibit geometrical isomerism. So, The rotation is restricted due to the presence of pi bond in alkenes. So all the atoms attached to the alkene lie in the same plane. Cis to butene, trans butene. Butene has geometrical isomerism as shown in the group. So let us discuss about the nomenclature of geometrical isomerism, geometrical isomers. So by looking at the isomers, we can tell which is a trans and which is cis. So all we need is trans means opposed, cis means on the same side. So it is not easy, it is an easy and visual way of telling two isomers apart. In the example of 1,2-dichloroethene, there are two similar groups present around the carbon-carbon double bond. So if all the substituents around the carbon-carbon double bond are different, for example, this is the example which we can say all the different groups are there. See, chlorine, bromine, fluorine and hydrogen. So in this case, the cis and trans cannot be judged by looking at the isomers. This is because the substituent attached to the carbon-carbon double bond are different. So the presence of more than two different substituents on a double bond makes it difficult for the geometric isomers to be named using cis and trans descriptors. So another way of displaying geometrical isomerism is EZ system. So in EZ system of nomenclature, the geometry of the isomers is determined by prioritizing the substituents on the two carbons of the double bond. The priorities of the substituents are determined by the atomic number, with atoms of higher atomic number having higher priority. The isomer E is denoted E if the higher priority group is present on the opposite side of the double bond. E is given from the German word Entingen, opposite. However, Z is denoted by the letter Z if the higher priority group is on the same side of the double bond. Z means zusammen, German word together. The letters C and Z are represented with a parenthesis and are separated with the remainder of the name with a hyphen. So, if we take the general example, determine the priority of A and B, determine the priority of C and B, C and D. A is higher than B, C is higher than D. So, if we say high and low, high and low, so in that case it is Z. If the high priority groups are on the same side of the double bond, then it will be given Z notation. If the high priority groups are on the opposite side, then it is given as E. So accordingly, this configuration is given Z and this is given E. The following procedure is adapted to denote the geometrical isomerism using E and Z descriptors. The group with higher priority on each end of the double bond is determined. The isomer is descriptor E if the higher priority groups are on the opposite side of the double bond. Otherwise, the isomer is denoted by the descriptor Z if the higher priority groups are on the same side of the double bond. The priorities of the substituent are assigned by CIP rules. Rank the atoms attached directly to the olefinic carbon, that is carbon containing double bond, according to the atomic number. Higher priority is given to the atom with higher atomic number. If the isotopes of the same elements are present, the upper priority is given to the isotope with higher mass. Say for example, deuterium is an isotope of hydrogen having atomic mass 2. It has just one proton, but still atomic mass is 1. However, it is not equivalent atom of ordinary hydrogen. Then these two compounds exhibit different